In this lesson, we're going to look at common problems and fixes in fitting linear regression. In the book, An Introduction to Statistical Learning, they mention 6 common problems, and they do mention that identifying and correcting these problems is as much an art as a science. So these common problems are: 1. Nonlinearity of the response predictor relationship, that is a relationship between the dependent variable and the independent variable. The second one is the correlation of error terms. The third one is non-constant variance of error terms. The fourth is possible presence of outliers. The fifth is possible presence of high leverage points. And finally, collinearity or multi-collinearity. So the first problem that we're going to tackle is to see if the relationship between the y and the x variables is linear, and we can do that in several ways. One is to check the scatter plot of y versus each variable, each x variable. Is it linear? Another plot that we can use is residuals versus fitted values. This is especially useful in multiple regression. And here we want to see no patterns. If the relationship is not linear, what can you do? So if you have these concerns, can you model using nonlinear relationships with higher order terms? Example, use squares or cubes, or use variance reduction transformations such as logs. Or what is driving the nonlinearity? Is that due to outliers? Or is there an important variable that you left out from your model? For example, age or gender of participants, let's say, in a study. Or was there systematic bias when collecting data? If that's the case, you need to redesign your data collection procedures. Checking residuals helps us discover very useful insights about the model and data. So you can examine the scatter plot of the response variable versus the explanatory variable. This is useful to do before fitting a model, and you can use that to identify any patterns. For example, in this scatter plot, using x squared rather than x as a predictor might be a better idea. In the residuals versus fitted values plot, the plot on the left, case 1, seems to be what we should aim for. Here in this particular case, the residuals are randomly located around the residuals equals 0 line. On the right side, in case 2, there seems to be non-linearities in this particular plot. Another plot to use is the normal QQ plot. So this takes the regression standardized error terms, sorts them in ascending order, and then plots their percentiles versus percentiles from a standard normal distribution with mean 0 and standard deviation 1. So that's the straight line, the standard normal distribution percentiles, and we're checking the regression standardized error terms. This is again a visual check. The x-axis plots the theoretical quantiles or percentiles from the standard normal distribution with mean 0 and standard deviation 1. So obviously half the data lie below 0, and the 0.95 quantile or 95th percentile is about 1.64 is about 1.64. So 95% of the data lie below 1.64. If the error terms after fitting the regression are normal, then their quantiles will be very close to the quantile line of the standard normal distribution. The next common error that we sometimes see is correlation of error terms. An important assumption is that error terms are uncorrelated. If they are not, then we have autocorrelation. So what do we mean? Knowing the value of EI should not have any influence on the magnitude or size of EI plus 1. This property is used to estimate the standard errors of the parameters of the model. If there is correlation in the error terms, then we have some problems. The standard errors will underestimate the true standard errors, confidence in prediction intervals will be narrower than they should be, and p-values will be lower than they should be, and we may have a sense of confidence in the model that is not warranted. So one test to detect autocorrelations is called the Durbin-Watson test, and that's available in R and other packages. The third type of problem that we could have in fitting linear models is heteroscedasticity or non-constant error variance. So this assumption is that the spread of the response around the straight line is the same at all levels of the explanatory variables. You may have non-constant error present, and you can detect this with the residuals versus fitted values plot. And if non-constant error is present, then hypothesis tests and confidence intervals can be misleading. So if there is this non-constant error or heteroscedasticity, then transformation of the y variable may be called for. Example, using the natural log of y or the inverse of y, etc. So here is an example of heteroscedasticity. The residuals are increasing with increases in the predicted value of price. Before we go on to the next lesson, here's a short quiz. If the scatter plot of y versus x shows a nonlinear pattern, then we should not change our linear model. False. Autocorrelation is the correlation between the EI variables. Answer is true. Heteroscedasticity means having constant error variance. False. Constant error variance means homoscedasticity.